Welcome back to ECE 320A, 48 hours. That's when our first exam will be. So the next time we meet in this classroom, you need to be ready to go for chapters 10 and 11, homeworks 1 and 2. Homework solutions, if you want to see a detailed solution or multiple solutions, those are available on D2L, and there are practice exams. If you're looking at old exam 2 practice exams from some previous summers, make sure that you don't worry about the last half of those exams. They're a little bit out of sync with what we're doing in the fall semester. I will quickly scroll through what the exam number 1 process is, and then we will move forward. Don't everyone leave. But this material that we talk about today won't be on exam 1, it will be on exam 2. But it will get you ready. Chapter 12, that's where you want to be looking after Thursday. So when you go home Thursday after the exam, when you're refreshed and all feeling good after the exam, you can start chapter 12 material. And that's what we are talking about today. We'll look at the definition. Show of hands. How many were able to see? Oh, show of hands, yes. Thank you. Show of hands. How many were able to see Laplace transforms in their differential equations class? How many did not see Laplace transforms in their different? So it's about a split, 50-50. We will, how many have seen Laplace transforms before? That's like show of hands, isn't it, sort of? How much have you seen that? We will become very comfortable, I hope, with Laplace transforms. We'll define Laplace transforms. We'll look at a few very simple signals in the time domain and what their associated Laplace transform looks like. We'll just present some basic properties, but this Laplace transform allows us to basically rethink about time domain waveforms in the frequency domain, and it allows us to think about operations, differentiation, integration in terms of no longer differential equations, but algebraic equations. And that's why everybody just feels warm and fuzzy about Laplace transforms when we start to get comfortable with them. We'll then look at some examples, one being how can we convert a differential equation into essentially an algebraic equation, and then all we are doing will be playing algebra. That's why you studied that in 3rd grade, so that you now know how to work with algebra. You laugh, but in my graduate class this semester we were worrying about 1 plus 2, and I said, see, I knew you would learn those skills or use those skills when you were learning those in kindergarten. Here is what you need to know for Thursday. You do get 1 sheet of notes. You can bring a graphing calculator, and I've listed some of those. Maybe you have the titanium. Isn't that sort of the TI-89 plus? Writing and drafting tools. If you want to bring some a straight edge or a protractor, those will be allowed. Did somebody bring their T-square? You don't probably need a T-square. Some of you are going, T-square, what's a T-square? Look it up online. I guess you can do anything now online. No cell phones, no computers. The last half are the no's. No, 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 no. 4 no's, no cell phones, no computers, no textbook, and no class notes. Let's now get into chapter 12, Laplace transforms. And these will be your friend for the rest of the semester. Laplace transforms are meant, and that's the key word, they are meant to be a simplifying transformation. Just with that sound, it just seemed to simplify the whole lecture. What we're doing then with the Laplace transform is we will convert time domain differential equations into frequency domain algebraic equations. Meaning we won't have to relearn KCL and KVL. We'll just learn or use those using, again, algebra, which is what we've done in the beginning part of ECE 220 with all resistive circuits. Now we will generalize. You went from all resistive circuits or DC circuits up to sinusoidal steady state. Everything's bouncing at a particular frequency. We just left 60 hertz with chapter 10 and 11. Everything is now done with sinusoidal steady state analysis, and that you'll have to be an expert on Thursday. What we want to do is learn how to play with the entire picture. Maybe constant waveforms, maybe sinusoidal, maybe they're playing together, maybe exponentially damped sinusoids. We want to be able to analyze and think about all of those different kinds of waveforms in a circuit problem, and Laplace transform allows us to do that. Here's the definition, and we will focus on a single-sided Laplace transform. By that means we're drawing a line in the sand and saying here's t equals 0, and then we're working for non-negative time, or from 0 up to infinity. That's what we mean by single-sided. Here's our definition. We will now define this capital F of S associated with a time domain lowercase little f of t. And this will now be transformed through an integral. But instead of just integrating f of t and from the time domain, we will actually scale that or weight it by a complex exponential waveform, e to the minus st. T is time. That's the argument of f. It's also one of the variables in this exponential, e to the minus st, and we're integrating with respect to time. And I said we wanted to cover non-negative values of time. We want to include all of 0. So we go a little bit to the left of time 0. We're at 0 minus. That allows for anything that happens at t equals 0, like an impulse, to be incorporated into this Laplace transform, and then we go all the way up to infinity. And that's the definition of a single-sided Laplace transform. What we're doing is we're taking this entire waveform for all time, we're weighting it by this complex exponential and boiling it down into some, let's say, rational expression or a function of the complex frequency variable s. We're looking at this entire expanse of time. I guess it's one-sided, so it's from 0 to infinity. We capture all of that in this integral, and now we boil it down into a capital F of s. And now we can play with algebra and not differential equations. Let's look at an example of a particular little f of t, a waveform as a function of time. Oh, and the notation, maybe I should just say what I'm using for notation before I get into the example. Capital F of s, that's the Laplace transform of a little f of t, and I might sometimes have this script L of f of t, and that is a shorthand way of writing that more complicated integral. Here's our example. Suppose that we have a waveform that looks like that. And what is that waveform? Does it have a particular name? It has a magnitude of 1 or of unity, and it steps up at 0. That's the unit step. And we typically might label that as u of t. Or you can think of this now, if you know how to find the Laplace transform of a unit step, you now know how to Laplace transform any constant. You just have to scale the result that we have for the unit step. And this example is illustrating this concept of Laplace transforming a signal, and in this case it's a particular signal, which is the unit step. But now we are Laplace transforming, trying to collapse all of this information, although that's not a lot of information, is it? 1 for all time. That's not that hard to capture in terms of a time domain waveform. If we now follow our notation, we now want to Laplace transform u of t, which we now can also call capital U of s. That's this integral from t equals 0 minus to infinity of u of t e to the minus st dt. What does u of t, that function of time, what kind of values does it take on over this window that we're integrating over? It only assumes one value, and that one value is actually 1. In this case, we can replace u of t with 1, and we will integrate again from 0 minus to infinity. Now we're going to move ahead a little bit from your algebra days. Now we're using calculus. Do you remember how to integrate? And the answer is yes. The correct answer is yes. You do know how to integrate. What's the integral of e to the minus st? Now s is a variable, but we're not integrating with respect to s. We're integrating with respect to t. S you can consider to be a constant now. We're not worrying about what s is. Does that look okay? And now we need to evaluate that at t equals 0 minus and infinity. We have that minus because the exponent had a minus sign in it, and we're now dividing by what's essentially scaling t in that exponential. If we had the integral of e of t, that's e of t. Now we have this e to the st, e to the minus st, and that's where we get the minus 1 over s. Again, we are evaluating this or integrating over time. S is like a constant. We have e to the minus s, and we're evaluating that at the upper limit. Really, I'm getting a little bit sloppy. We would say that's maybe capital T, and we're looking at the limit as capital T goes to infinity, but that's what I'm implying by this notation, minus that argument evaluated at the lower limit. If we do take the limit, and we are assuming that we evaluate this for values of s that allow these results to make sense, or for this integral to converge. So we're evaluating this when s is positive. If s is positive, what's the first term in that bracketed expression? If you looked at e to the minus t as a waveform, what does that look like? You see this curve, and what's it doing at large values of time? It's going to 0. So we now have minus 1 over s. That's 0. Where does it start? What's e of 0? That's 1. Which now we've derived the Laplace transform of a unit step, and that's now just 1 over s. We will eventually start talking about poles and zeros. And you could even think tic-tac-toe. The poles will be x's and the zeros are zeros. We'll talk about poles and zeros. The poles are the values of our numerator expressions that cause that, the poles are the roots of the denominator expression that go to 0, or the values of s that cause the denominator to vanish. The zeros are the values of the numerator values of s that cause that to vanish. How many zeros do we have? Is the numerator even a function of s? No. So we have no finite zeros. Do we have any values of s that cause the denominator to vanish or to go to 0? Yes, this one's too easy. It's hard, but when s is equal to 0, the denominator vanishes, so we have a pole at the origin. We have a pole at 0. We'll talk more about that later, but right now I want you to just know that we have two domains. We have a time domain and we have a frequency domain. And I'm going to be moving back and forth between those domains. The waveform is in the time domain. That was constant. It was just flat at 1. In the frequency domain, it has a matching pair, so if I was over there at the same time, we could just be representing the same waveform. It's just I'm in the frequency domain, and it's in the time domain over here. Here it's 1, here it's 1 over s. That's all there is to it. And you'll start to learn these tables of pairs, and you can go back and forth between frequency domain and time domain. Let's look at one that's just a slight variation on that example. Suppose that we delay the unit step. Functionally, that's now u of t minus t naught, where t naught is some positive number. Say u of t minus 10. The unit step is going to be 1 when its argument is non-negative. When is that argument non-negative? As long as t is bigger than t naught. Then we'll have a value of 1. In a picture, that means that here's t, here's u of t minus t naught. What does that waveform look like? I'll do the hard part. It's going to have a value of 1, right? U of t. We haven't scaled that waveform, but we said that the argument, when it's non-negative, that makes this waveform be equal to 1. And when is this argument non-negative, or when is it positive, to be a little bit less general. When t minus t naught is greater than 0, so now this is going to be t minus t naught non-negative. That means that t is greater than or equal to t naught. Wherever t naught was, it's only going to be 1 for values of t bigger than t naught. That's supposed to be a flat waveform at the same constant value. Let's now see what that waveform looks like in the frequency domain. It looks pretty similar to the original unit step. It's just now it flipped on. You went and flipped the lights on 10 units of time later. And if you were looking for points on an exam, you would say, oh, I'll just plug that into the definition. He'll give me some points. Which means that the definition, we're integrating from 0 minus to infinity of u of t minus t naught e to the minus st dt. We always put our waveform into the integral. We weight it by this complex exponential, e to the minus st, and then we integrate that scaled waveform over non-negative time. That doesn't quite look like our earlier integral because now we don't have u of t, we have u of t minus t naught. But you remember your calculus, you can force things to look like they did before. Suppose we define a new variable tau that's the argument of u. Now if we needed to, we could find or replace t wherever it occurs in that expression with what it equals based on how we've now defined tau. If we solve for t, we find that t is tau plus t naught. Remember, t naught is a fixed number. If that's the case, what is d tau? If t naught is constant, and now we differentiate or look at the differential of tau relative to t and t naught. What's the differential of t? What's the differential of a constant? So there we're done. Wherever we had a dt in our integral, we'll replace it with d tau. What about our limits of integration? We had one limit that was t equals 0 minus. Now if we use what's in the box, if we plug in t equals 0 minus, what is tau going to equal? Minus t naught. The lower limit now is minus t naught. What about when t goes all the way to infinity? What's tau? That's also infinity. Now we've done a change of variable in our integral. We can now rewrite our Laplace of our delayed unit step. That's now this integral from tau to from minus t naught up to infinity, u of tau e to the minus s, and now we are replacing t with tau plus t naught, and dt was the same as d tau. That looks a little messy, but we can clean that up by using our understanding of exponents. E to the quantity x plus y is equal to e to the x times e to the y. This now we can separate and say that that's e to the minus s tau, and it's e to the minus s t naught. That product is equal to that factored exponent. We're integrating with respect to tau. S and t naught are not a function of tau. That can be slid outside the integral, that e to the minus s t naught. Integral from tau equal minus t naught to infinity, u of tau e to the minus s tau d tau. Let's make sure that we're okay. I'm going to separate that integral into two pieces. I'm going to have one integral from t equals 0, tau equal minus t naught up to 0, u of tau e to the minus s tau d tau. And then the other half is going to be from 0 to infinity, u of tau e to the minus s tau d tau. Everybody comfortable with that calculus operation? We're just separating this integral into two pieces. What is this u of tau between minus t naught and 0? What's its numerical value? Now you would replace tau in the argument with a negative number. And what did we say the unit step functionally is equal to when the argument is negative? It's 0. Wow, we've simplified this integral. If that's 0, now we integrate 0. That's easy, isn't it? That's just going to be 0. And what's the right-hand side look like? Or the right-hand half of that split original integral. That should look just like the previous examples Laplace transform. It's just now we've replaced t with tau. But that's just the integral of a unit step. And we've already computed that to look like what? 1 over s. Thank you. See how easy this is? The unit step over here in the time domain looks like 1 over s in the frequency domain. And that's what you did with this piece right here. Let's now put those together. We now have e to the minus s t naught. That first one was 0, and this one's 1 over s. We now have then that the Laplace transform of a delayed unit step is e to the minus s t naught over s. That looks somewhat like the Laplace transform of our unit step. That was just 1 over s. We've now simply scaled that 1 over s by this complex exponential. T naught is a constant, and s is a complex variable. That particular example generalizes in that if we take the Laplace transform of any function, f of t, and then we want the Laplace transform of a delayed version of that same function, then we can actually find the Laplace transform of the delay by simply scaling the Laplace transform of the original f of t, scaling it by e to the minus s t naught. And that's an operational transform that you might have in another table. Meaning if you know the Laplace transform of f of t, it's pretty easy to find the Laplace transform of a delayed version of that waveform. You simply scale it, and somebody needs to wake me up. That's supposed to be t naught, right? Don't be asleep in 48 hours. Make sure you get some rest in the next couple of nights. Okay? It's better that you're well rested than spending all-nighters and come in and go, oh, was there an exam today? Please get some rest, okay? Now, let's look at some properties. I know that will go over like a lead balloon, won't it? But I told you. And eat well-balanced meals. Boy, do I sound more and more like a parent? Sorry. Now you're really upset. What are some properties that we can see that are very useful for the Laplace transform? One is homogeneity. That's basically a fancy word for saying if you scale a waveform by some constant A, then that's the same as scaling the Laplace transform of that waveform, which we are calling capital F of S, by the same constant A. Here, A is just a constant, i.e., or that is, A is not a function of t or f of t. A is just a constant. It's not a function of time. Then we have homogeneity. The other nice property that Laplace transforms enjoy is superposition. Which means if we have one waveform, let's call it f sub 1 of t, and we add that to a second waveform, f sub 2 of t, then that is going to give us in the frequency domain what we would expect, the sum of those two Laplace transforms. These linearity properties, homogeneity and superposition, allow us to now convert differential equations into algebraic equations. And you, I'm sure, like to solve algebraic equations more readily than differential equations. Which now says that each circuit element, and here think R, L, and C, or circuit variable, maybe you have some dependent sources. These different elements and variables can actually be transformed by themselves or separately, and then added together. And that gives us our main result. That is, differential equations can be transformed into algebraic equations, and we can now do algebra to solve these more complicated differential equations. We've looked at a very basic couple of examples for waveforms. Now let's look at how this Laplace transform can actually help us transform operations in the time domain into other looking polynomials in the frequency domain. So let's look at the Laplace transform of a derivative of an operator. What we're wanting to do now is Laplace transform the derivative of f. And that actually, let me just write that down. That's s, the complex frequency variable, times the Laplace transform of f of t minus the little f evaluated at 0 minus. Meaning there now is some initial condition that you can include or incorporate when you're Laplace transforming a derivative. And that argument, 0 minus, is t equal to 0 minus. What was your waveform's value at time t equals 0 minus? You take that away from the product s with the Laplace transform of capital F of s. Now we put on our 2-year-old cap, y, and we ask why. Where did this come from? Where's the Laplace transform of a derivative coming from? Now we get to play even more with our calculus. We now want to Laplace transform df of t dt and I might write that many different ways, but now based on the formula, that's this formula from t equals 0 minus up to infinity of the function that we're trying to Laplace transform, which is f prime of t, scaled by this complex exponential e to the minus st and integrating over time from 0 minus to infinity. Now, how do we remove derivatives from under an integral or within an integral? You remember? This was your favorite part of second semester calculus. Maybe I should say it was the part of that class that was your favorite part. Integration by parts. That's how we're going to do this. That was your favorite part, wasn't it? Wow, that stirred up a little emotion. Let's now remind ourselves how we do that. Now we need to identify V and dW, for example. Suppose we let V be e to the minus st. Then dW is going to be what is left in the integrand of that integral. And that's now f prime of t dt. Again, we're trying to rewrite this as some combination of terms that do not involve the derivative. And by assigning dw to be f prime, now we can integrate that pretty easily. What is dv? What's the differential of e to the minus st? Or what's the derivative, and then we'll multiply both by dt? Everybody heard that, right? It's minus s e to the minus st dt. That's the differential of v. What's w? All I have to do is say integration by parts and the whole class parts, right? This is f of t. Now we can do this Laplace transform of the derivative of f. This is now integrating by parts. This, let's say we start with the integral of v dw. That's what we identified, v and dw. Do you remember what that equals? Oh. It's the product of those two variables evaluated at the limits, if there are limits, minus the integral of w dv. That's the structure, and now let's plug in the pieces that we have for our particular example. V was e to the minus st, and w was f of t, and we evaluate from t equals 0 minus and infinity. Then we have minus this integral from t equals 0 minus to infinity of w, which is f of t, dv, which is minus s e to the minus st dt. And now we simply have to evaluate that right-hand side. Let's look at the first piece. That's e to the minus s at infinity, f of infinity. And we're assuming that f is well behaved at infinity, which means it's bounded, minus e to the minus s0, f of, well, maybe I should plug in the actual t at 0 minus. And then in the right-hand integral, I have a minus, and that minus inside the integrand I'm going to pull out so that I now have a plus, and let me pull out the s. That's not a function of t. And I now have this integral from t equals 0 minus to infinity of f of t e to the minus st dt. And that should start making you feel very comfortable. This little piece right there. What is e to the minus s at infinity? We'll say pick the values of s where that is defined. As long as s is positive, that's going to vanish. So that's going to allow this guy to go to 0, and we said that f, our waveform, is well behaved. It's not going unbounded at infinity. What's e to the minus s0? That's still 1. E to the 0 is 1. And what are we left with? Now we have, in the first bracketed expression, we have minus f of 0 minus. That's the function of time evaluated at t equals 0 minus. And what's in the blue bracket? That's the definition of our Laplace transform, and we just have to scale that by s, so that we now have s times capital F of s, and that's what we were trying to show. We now have shown that the Laplace transform of a derivative is equal to s times the Laplace transform of little f of t minus f of 0 minus, where that 0 is time t equal to 0 minus. Now we have a lot of tools. Meaning, I'm sure you woke up this morning thinking, you know what, I would really like to solve a second-order differential equation. Or were you dreaming about that and you just woke up and said, oh, that was a great dream. Oh. So let's look at that. Let's look at a second order, x double prime plus 3x prime plus 2x of t equaling v of t. Now, let's get a little silly. What do you see there? And I expected somebody to say hypotenuse, right? But now maybe you actually see a circuit, a second order circuit. What's a second order circuit that might actually be governed by that second order differential equation? an RLC circuit. You have an energy storage device in an inductor. You have an energy storage device in a capacitor. You now have a second order circuit. It may have that as a governing differential equation. Maybe that describes, maybe X is the current flowing through that circuit. And little v of t is the voltage waveform, which we aren't going to say what it is. Maybe it's a decaying exponential. Maybe it's a exponentially damped sinusoid. See all these fun words and phrases we get to use now? Maybe it's a constant. Maybe it's an impulse. But v of t, we are going to just let it be whatever we want it to be for now. It's a generic waveform. Now, if you are talking to your friends about this, well, at least you guys have friends. So, here, this equation is a linear time invariant. This is what you're going to say when you walk up to somebody. Oh, we were just solving a second order linear time invariant differential equation. Let's go enjoy some lunch. This equation is a linear time invariant, which we will abbreviate because I know you want to tweet this. We'll just tweet it as LTI, linear time invariant, differential equation. So you could just say, oh, we were working on second order LTIDEs. Quick to tweet. So let's do that. Now we want to take this time domain differential equation where? In the frequency domain. See how easy this class is? All you have to remember is where I am. Time domain, frequency domain. We now are in the time domain. We want to go into the frequency domain. So now we're not, over here we have t's. Over here we have s's. So let's get some s's. Again, we're being very creative with our choice of variables, s and t. They're very far apart in the alphabet, aren't they? No, but let's now Laplace transform that both sides of this differential equation, this second order LTI-DE. We now have the Laplace transform of x double dot, or x double prime, I'll do either one probably, plus 3x prime plus 2x, and there is our superposition property. We can do both sides without harm, and then we will Laplace transform this yet to be determined waveform little v of t. If we do superposition a little bit more, we can factor all of those or take the Laplace transform of all three of those terms separately. So that now we have the Laplace transform of the second derivative plus, there's our homogeneity, 3 times the Laplace transform of x prime plus 2 times the Laplace transform of x of t, and that's equal to, and we will just call that capital V of s, the Laplace transform of little v of t. We haven't yet determined what that is, or stated what it is. Now, we just learned or derived how to Laplace transform a derivative. Now we have a double derivative. Well, let's just think that's a derivative differentiated. What would be the Laplace transform of a derivative? That's s times Laplace transform of the original waveform, which in this case is just one less derivative than what we had, minus the initial condition of that waveform at 0 minus. That's the first piece of this left-hand side. We still have more to go because we don't want to leave that derivative in the Laplace transform, and now we know how to Laplace transform that expression. What's the second piece? We have plus 3. Now we do have just a single derivative. That's s times capital X of s minus x of 0 minus plus 2 times x of s equaling v of s. We're almost finished. We just have to get rid of this last Laplace transform of a derivative, but we know how to Laplace transform a derivative. That's just s times the Laplace transform of x minus x at t equals 0 minus. And all of that will be scaled by that s. Let me write that down, hopefully. This is now s times s x of s minus x of 0 minus x prime of 0 minus. All of that in blue is the Laplace transform of a second derivative. Plus 3s x of s minus 3x of 0 minus plus 2x of s equaling v of s. Now, let me collect terms. Let me collect all of the coefficients that scale capital X of s. And now I could ask you, what do you see? What's the highest power of s that scales capital X of s? Now we're just doing algebra. We're not doing differential equations. I mean, we are doing them implicitly or indirectly. Do you see the s squared, s times s? We have an s squared. Then we come to our next capital X of s, and that's scaled by 3s. Then we find our next capital X of s, and that's 2. Now we have some little x's at 0 minus. We have 2 of those terms. We have one that's minus s, and we have one that's minus 3. Let's factor out the common minus, and we have a minus s plus 3x of 0 minus. We have a minus x prime of 0 minus, and all of that on the left-hand side is equal to capital V of s. What are we trying to find? Did you get lost? Yeah? It's an honest answer. Here was our second order differential equation, and we said this might correspond to an RLC circuit. And what did we say X might be? Maybe the current flowing through that RLC circuit. We might like to know that current satisfies this second order differential equation, but what does X of t look like in the time domain? Little x of t, what's that look like? It'd be nice to know. Is it some exponentially damped sinusoid? Is it a constant? What does x of t look like? What's the current look like in that circuit? That's what we're trying to find. We're trying to find it by first starting with our differential equation, transforming that into the frequency domain, doing some algebra. Didn't that look like algebra? So you're doing this algebra, Then you solve for capital X of S. And then what do? You take it back over here by inverse Laplace transforming, and now you have little x of t. That helped, didn't it? Thank you. So now we have capital X of S over here. We need to solve for that. And once we have an expression for capital X of S, then we can figure out how do we inverse Laplace transform that to get back over into the time domain. We want little x of t. We can find capital X of S. Let's solve for that. If we solve for capital X of S, do you see we can take the initial conditions onto the same side as what our, let's say, our voltage supply equals in the Laplace domain, capital V of S, and then we divide all terms by this quadratic in S, S squared plus 3S plus 2. Meaning we now have capital X of S is equal to S plus 3 x of 0 minus plus x prime of 0 minus. Those are all our initial condition terms. And then we have plus capital V of S over that same denominator. That's now our expression for capital X of S in the frequency domain. And the nice thing about dealing with one-sided Laplace transforms, do you remember what one-sided referred to? What interval of time were we dealing with? Minus infinity to infinity? 0 to infinity. Just one side, not two-sided. So the sides refer to t equals 0. We had one side from 0 to infinity. We would have two sides if we went from minus infinity to plus infinity. We're just doing the one-sided Laplace transform. The one-sided Laplace transform is nice because the transform is unique. Meaning if you give me an x, little x of t, and compute the capital X of S, there's only one little x of t corresponding to that capital X of S. It's unique, the transform. The one-sided Laplace transform is unique, which is why we can use the tables to look up the relationship of these pairs. Another way of saying that is if we're given capital X of S, that's what it looks like in the frequency domain. We can find what it looks like in the time domain, little x of t. And you need to really pay attention to this notation now. How do you think we notate the inverse Laplace transform? The Laplace transform looked like this, didn't it? If we want to invert that, we get very creative and we put an inverse on the script L. Which means then, from our example, little x of t, and that could represent the current in our RLC circuit. That's the inverse Laplace transform of capital X of S. And that capital X of S had two parts, and we can separate this inverse Laplace transform into two parts. We can say the inverse Laplace transform of S plus 3 x of 0 minus plus x prime of 0 minus all over s squared plus 3s plus 2 plus the other half of that right-hand side, which was 1 over s squared plus 3s plus 2. I'm trying to be very explicit that that capital V of s is some function in the frequency domain corresponding to a generic waveform, maybe a voltage supply, little v of t in the time domain. If you look at these two pieces on the right-hand side, this piece, you can see that the only thing that depends on other than values of s are initial conditions on your current. So this would be, what's the current at time 0 and what's the time rate of change of my current at time 0. If I have those values and I weight them and divide by that quadratic, I now have the Laplace transform of that circuit's initial condition response. This, when we take it into the time domain, will be the response of our circuit due to initial conditions. And the second half of that two-term right-hand side, this that I've now highlighted in the black loop, that's the response due to how we excited the circuit to begin with, or this excitation function, the excitation function being little v of t. Now, what do you think we're ready for at this point? Besides a nap, I'm trying to keep you from napping, we now have a quiz. What's the quiz? Let me give you a circuit. And if you want, you can tweet this to your friends. I want you to find the governing differential equation for that circuit. Now, I've already given you quite a bit relative to this story, this quiz. But I might want you to, after your exam on Thursday, think about how you would approach this problem. What do you have in that particular circuit? What kind of elements? What's a resistor do? What's the current voltage relationship of a resistor? It's not that hard. I'm asking it in a way that you're going. But I'm really asking you for Ohm's law. What's Ohm's law of a resistor? What's the time domain relationship of voltage and current on a resistor? That's Ohm's law. What's Ohm's law for a resistor? V is equal to IR, and you need to know that until you retire, right? If you're an ECE major, you know Ohm's law. Another motive for striking it rich and retiring in 2 years, right? And you only have to know Ohm's law for 2 years instead of 32, or whenever you retire, 52 years beyond, so you're working until 75. You're in electrical and computer engineering. This is a fun major. We're in the frequency domain. We're in the time domain. Who knows what domain you guys are going to be living in, right? Now, we don't have anybody. Okay, good. So now you know the R, Ohm's law. What about the resistor? I'm sorry, the inductor. What's the current voltage relationship of the inductor? Oh, this will be useful Thursday, maybe. Eli. Right? Eli. That tells you all you need to know about the time domain waveform or the current voltage relationship of an inductor. Eli. Capacitor, ice. Now, if L and C currents and voltages are related by differential relationships, that means that the time rate of change of certain variables, currents or voltage, are influencing the current and voltage, which means you kind of have some history or past or memory in these circuit elements. You have no memory in a resistor. You give it a current, it gives you a voltage instantly, proportional to the current. But in Eli and ice, that's a little different. Now they are memory storage devices, the inductor and the capacitor, or they're energy storage devices. They store energy. In the magnetic field, it expands and collapses. That's the inductor. In the capacitor, it has an electric field, and it stores energy in that electric field. We're thinking about this. If somebody asks you this on an interview, you could start going through this thought process. You're going, oh, gosh, second order differential equation, he expects me to solve that? Okay, let's look at this circuit. L and C, I have two energy storage elements, or two energy storage devices. Does that tell me anything about the relationship in the time domain of this circuit? You now have derivatives because of Eli and ice, because of the L and the C. If you have derivatives, what kind of an equation are you going to expect? Differential equation, right? So now you have a differential equation, and if you have two energy storage devices, how big do you think that differential equation is going to be? What order? Second order. This is pretty hard, isn't it? 2 and 2. So two energy storage devices implies we have a second order differential equation. And because we are assuming that L and C and R do not vary with time, this is time invariant and it's linear. It's an LTI. We have a linear time invariant second order differential equation, which means in your interview you're saying, well, if it's a second order differential equation because of the two energy storage devices, in general, let me just show you the general differential equation that this must satisfy. It's alpha 1, let's say V sub C double prime, capacitor's voltage differentiated twice, plus alpha sub 2 V sub C prime, plus alpha sub 3 V sub C of t, equaling beta V of t. And that's now a way to generalize the behavior of this RLC circuit. If you know how to solve second order differential equations, you now know how to solve this circuit problem. Now, how would we solve this circuit problem if you just, well, what would be one technique to buy yourself some time in your interview question? How would you start to show that you could solve this equation? I was too far into the left half plane of my frequency domain. KVL. See? I just have to give you some time and you can start to solve this. If we did KVL, we could be saying, just in general, you might say, well, let me label these voltages. There's the voltage drop across the inductor. Here's the voltage drop across the resistor. And here's the voltage drop across the capacitor. Now I'm assuming that I have some current, let's say I sub L of t, flowing through that circuit. And actually what those red variables are the variables that you'll probably want to be writing your equations in terms of: inductor currents and capacitor voltages. Hint, hint. And that's coming to us from Eli and Ice. If we look at Eli, well, maybe let's do KVL first, as suggested. If I now write a KVL equation in terms of those V's, what does KVL provide me with? Let me start in the lower left-hand corner. Now I'm just going to start reading off those voltages that I've labeled. And I'm going to read those off with the appropriate sign, meaning how do I enter that variable? Either the minus or the plus sign. I'm going up from the bottom on V of t. I enter the negative sign first. I have minus V of t plus V sub L plus V sub R plus V sub C, and then I get back to where I started. That algebraically needs to sum to 0. There's KVL. I now have minus V of t plus V sub L of t plus V sub R of t plus V sub C of t is equal to 0. This is going to be like falling off a log. It's going to be so easy. Just don't get hurt. Now, you found KVL. What about Eli? Eli is going to allow us to find the current I and the voltage E relationship on that inductor. And the order is important. We have V first, then we have the element L, and then we have the next variable, and we differentiate that second variable. Meaning Eli tells us that we have V sub L, the voltage of our inductor, is equal to L di sub L of t dt. And that L, V sub L, can go in there. What about ice? Again, this gives us the capacitor's current voltage relationship. We have the capacitor current, I sub C of t, is equal to C dV sub C of t dt. And somehow we want to use that to get rid of currents and or we want to write this as a second order differential equation at some point. But what do we know if we go back to this particular circuit? How is the capacitor current related to the inductor current? There's I sub C of t, isn't it? That's exactly the same current as I sub L. Maybe we can use that. Let's see how much further we can go. We still have 47 minutes, 47 hours. All right, you have an exam on Thursday. We'll pick up at this point in a week, but you can start studying over the weekend on Chapter 12. Good luck studying for exam number 1.